Yes, students, as we have seen in the previous lecture, the motional EMF and proof of Faraday's laws. In that lecture, we have seen whenever there is the change in the magnetic flux linked with a coil or circuit, the induced EMF is developed and a current flows called induced current if circuit is closed. Now in today's topic, mutual induction. It is a phenomena of producing EMI when the two coils or circuits placed close to each other. When current changed in the one coil or circuit, the induced current is developed in the second one. The first circuit by which we change the current is called primary circuit, and second one is called as the secondary circuit. So this is the mutual induction, and we'll see by using the diagram. So this is battery and this is a rheostat. This is battery and this is key. So the current flows in the circuit. This is current I. Now another circuit or coil which is placed close to the first one, which is having only galvanometer. So what happens when key inserted and current begins to flow? So the current increases from 0 to maximum. So whenever the current increases, the magnetic field produced by this coil also increases, and magnetic lines of force passing through the nearer coil like this. So the magnetic flux is linked with this secondary coil. So a current is produced in this second circuit or coil, and direction of current will be in the opposite direction. So it will oppose the increase of the current in the primary coil or circuit. So current will flow in this direction. So either the current increases in this or we insert the key. So this is the mutual induction. There may be the second case when in this case now this key is released. When key is released, so current becomes 0 in the primary coil or circuit. So current decreases from maximum to 0. So there is no current. The magnetic lines of force passing through this also decreases. So magnetic flux linked with this coil also decreases. So the current developed in the second circuit or coil, that will oppose the decrease of the current in the primary. So this current flows in the same direction to oppose the main current. So initially the current is flowing in this direction. So to oppose this decrease, so current will flow in this direction. It is like this. So galvanometer needle will be in the opposite direction of the first one. So this is called primary and this is called secondary coil. This is primary and this is called secondary coil. So this is the mutual induction. Now the coefficient of mutual induction. So coefficient of mutual induction suppose there are n turns in the secondary coil. Suppose ns are the number of turns in secondary coil and flux passing through one turn is phi for second. The total flux passing through this whole coil, that is ns phi s, and this is called flux linkage. This is called flux linkage or total flux linkage. This flux linkage is directly proportional to the flow of current in primary, that is IP. So removing this proportionality, ns phi s equal to m IP, or we can write m equal to ns phi s upon IP, where this m is a proportionality constant and called as coefficient of mutual induction. Coefficient of mutual induction. And we can define this. So this coefficient of mutual induction is asked in the board examination in half mark, and in half mark the unit of this. So how to define this? If IP equals to 1 ampere, so M equal to ns phi s. So coefficient of mutual inductance is equal to the total flux linkage when current of 1 ampere flows in the primary coil or circuit. So this is called coefficient of mutual induction. Now the next, we can define this coefficient of mutual inductance in terms of Faraday's laws. According to Faraday, the induced EMF developed in a coil or circuit. So here we have the secondary coil, the induced EMF developed is ES, and it is equal to the number of turns delta phi upon delta t. So this is also called as rate change of magnetic flux with n turn or ns turn. So this is the induced EMF and here it is negative sign. We can also write this induced EMF as ES equal to minus NS phi S and dt. So this NS is taken inside, so it is NS phi S, and we have seen this is the total flux linkage and it is equal to Mi, since NS phi S equal to Mi P. Therefore, ES equal to minus MIP upon dt, or it is equal to minus M dip upon dt. So M is independent, so we can take it out, so it is like this, or we can write M equals to minus ES dip upon dt. This is also coefficient of mutual inductance, and we can define here. If dip upon dt equals to 1 ampere per second, so M equals to minus ES. So according to Faraday's laws, the coefficient of mutual inductance is equal to the induced EMF developed in the secondary coil when the current changes in the primary coil at the rate of 1 ampere per second. So this is all about this coefficient of mutual inductance, and unit of it is measured in Henry, or it is represented by H. So generally Henry is a bigger unit, so we measure this inductance or mutual inductance in a smaller unit, millihenry and microhenry. Now the self-inductance, or one application of this we'll see in the next